Okay, so I forgot to record the first half of the class. So sorry for that. But anyway, so the idea. We were talking about this at the last moment. We were talking about these very new works about the rigorous proof of blow up in a different situation. So what I could suggest, so if there is one of the students who had a mathematical background and would like to study the idea of the proof of these proofs for the C1 alpha, for the existence of blow up for C1 alpha solutions, and give a presentation for like 40 minutes explaining the idea, that would be a good project for the course. So if someone would like to do that, please send me an email. So now let's do break until 16, and then we continue. So if you have any questions, just can ask.
Hi, Professor. So I have a question.
Yeah, Andre.
So in this theorem 1, so this blow up is for a C1 alpha solution, so it's a weak solution, right?
No, it's strong solution. Strong solution, because the Euler, in Euler you only need one derivative. So C1 alpha means that
True.
it's continuously differentiable.
That there's no Laplacian, right?
So you can still satisfy equations in the original form. So it's not a weak solution.
Okay.
We will be talking about weak solution later, but this is all about strong solution. It's strong solution, but only it's not a C infinity solution. So it has a singularity in the derivative, and apparently this is very important for the proof. So it doesn't give us very clear understanding whether there will be something better. Doesn't give a clear understanding of the infinity case, but anyway, it's already very good step forward. Okay, so we can continue. So as I said, sorry forgot to press this button to record. So please, if we have any other Google Meet class, so please, if you remember, please recall me to record. No, I always forget. So, oops. So what we will be continuing to do now is, since we cannot solve the problem for the full Navier-Stokes or Euler equation, so we can try to do this for the simpler models, which share some properties of the original model, but simpler. So simple in the sense that we either can prove or we can make a very, very clear numerical simulation. So either one, or we can construct any theory which can then be extended to the original work. So the probably most popular toy model of the Euler and Navier-Stokes, and essentially of the turbulence in general, is a shell model of turbulence. So let's introduce this model now. So the idea is to decrease substantially a number of variables from infinite dimensional space to some, well, at least to the smaller dimension space, keeping the structure. So if we want to have it a model which is simpler but keeping the structure, it means that we should keep some of the properties of the original system, which means that we should keep some symmetries. Maybe all, maybe not. Conservation laws. Etc. So usually the idea is that you try to make a simpler model that keeps the important properties. So if you are lucky, in the sense that if you're lucky to keep the right properties, then you hope to understand to create theory for this simpler model, which then can be extended to original model. So for this, you could really, it is important to select right properties. So to be lucky in a sense. Okay, so with shell model, what it does is that instead of having the infinite dimensional space, we consider a sequence of shells. So a sequence of shells means that sequence of, let's say in 3 dimensions, can be spheres. So that each next sphere is lambda times bigger than the previous one. So we have a number of shell scales of the, let's say, radius ln, which is lambda minus n. So usually we consider lambda to be 2. So it means that we have the first scale is 1, then the next scale is 2, the next scale is 4, etc. So the geometric progression. So the geometric progression of scales, and to each scale we associate shell variable, shell speed, or shell velocity. And it will be just a number. And we will see that we will derive the equations by similarity with the Fourier transformed equation. So this number will be complex. Okay, so this will be so. In other words, we will have shell numbers, which are integer, and for each shell numbers we will have the state of the system will be just a collection of all shell velocities for all shells. So you see that the system is already much simpler. So instead of the field of velocity defined at every point, we just define each number for each sphere. So this is an idea. So why is this? So why geometric progression? It is because of scale invariance. So scale invariance, it means that if you multiply, so if you take any scale and you multiply by lambda, it still become a scale. So you can, so the geometric progression is scale invariant. So you can multiply by any number and it still will be just the same geometric progression, right? So this is scale invariant. The scale invariance is probably the main, as we will see, it's one of the main symmetries that we need for understanding turbulence. Okay, so this is our model, which will be constructed around these complex variables. So now, how to construct how to construct is in order to understand how to construct, let us return to the Navier-Stokes equations. So just remember what are they? So du dt plus u grad u or minus grad p. I will write the viscosity. So usually in this field, people don't write viscosity. So density is 1, and if you consider velocity characteristic size to be 1, then Reynolds become 1 over nu, right? So that's a setting. So this is Navier-Stokes equation and incompressibility condition together. So this is an equation. So now consider the Navier-Stokes equation in the box. So we consider the box, and let the box we consider the box which is size of 2 pi cube. No? So it's a box where each side is 2 pi. And periodic boundary condition. So in that case, we can make a Fourier transform. Remember, so the Fourier transform. So for each field, so we can make a Fourier transform in space. In space. So Fourier transform in space. And Fourier transform in periodic domain, it's actually Fourier series, no? Fourier series. So we can write a Fourier series for the function u. So it's sum of the Fourier coefficients, which depend on time, and this is by exponent e k x. So where all k are wave vectors which are dimension 3, which is with integer components. So it's wave vectors. So this is Fourier series for the velocity field. And then remember that whenever you make Fourier transformed, what happens is that derivative, the gradient should be substituted by ik, right? So all the just derivative is always substituted by multiplication by imaginary union, not multiplied by wave number. Then Laplacian is become minus square of the norm. Also, the product of two functions become convolution of the Fourier transform, etc. No, so let's just remember what the Fourier transform is. So the Fourier transformed Navier-Stokes just become like d uk dt. Just you make this substitution. And then you have incompressibility condition that u should be orthogonal to the corresponding wave vector. So this is Fourier transform equations, and you can also describe pressure. So if you take ik and take a scalar product with Navier-Stokes equation, so what it gives, and use the fact that this incompressibility condition, what you get is, you see the first term is 0, right? Then you have this, I will cancel with I, it will give minus, then it will be k, uk, k, uk equal, I'll look at squared pk. So this gives you pressure, just like we did some time ago. The pressure will be minus you can write it in different form, but anyway, so you have an expression for pressure, and what you see is that both this term and this term, right, because of the last expression, so all these terms tell that these terms are quadratic in Fourier variables and first order in wave vector. So this is a structure we want to keep. So the idea of shell model is just to keep the structure of this equation by, when we take a shell model, what we do, we have to make substitution. So we substitute k by kn, which is inverse to the length. So in other sense, it's lambda n. Then we substitute uk by the un, which is our shell variables, which means that just writing exactly the Navier-Stokes equation for these new variables, what you get is that the time derivative should be the term which is quadratic in un and first order in Kn, right? And then what's left is minus nu Kn square Un, just directly the viscous term. So this is a general form of the of essentially any shell model that you can have. And the difference between shell models is how you choose the quadratic form. Right? Okay, so now let's try to choose the quadratic form. And of course, there are many ways to choose the quadratic form. So what the idea is to choose the right quadratic form, which gives the properties of the systems that you want to study. Of course, this was done after many different tries. So there are two different popular models. So there are several popular models, but the two models that we will consider models. So the first model that really showed very well the properties of the turbulence that we will be talking later is what's called Gledzer Hitani Yamada, or abbreviated as GOI model. And the choice of this quadratic form, which we can call Bn. So the choice of the quadratic form was I, imaginary unit, by some constant, Kn plus 1, Un plus 2. So what is you need to make some combination of some quadratic form with respect to the velocity. So this is exactly what we're doing. And linear with respect to the wave numbers. So this is the suggestion that was done. And all complex conjugated. So star will be complex conjugation in our case, in our study. So complex conjugation will always be a star. And another popular model was a Sabra model. Well, Sabra doesn't have any meaning. It's mainly a joke of the authors. But anyway, so that's if you know Hebrew, you can understand. So the term had very similar form, but slightly changed, and this change is actually quite useful. So it made properties of solution better. And the only change is how you put the change was just on the way how you put where you put complex conjugation. Just a second, I think I'm. Okay. So where you was putting complex conjugation. So this plus B. Okay. Too many. It's going plus 1, 2, 1, 1, 2, 1. Let's start here. Plus 1 minus 1, and here should be star minus C. And that's it. So essentially the only difference where you put star. So instead of putting star everywhere, you just put star on the two specific components. So there will be so there are two different models, which both are good, but properties are slightly different, and Sabra model is slightly more advantageous in some respects. Okay, so there are two models, and this model has parameters. No, the parameters A, B, and C, which are all real. Okay. So what left is to find what are the values of these parameters. No? So the first. So okay. So remember that what is the. So now our model. So the shell model becomes dun dt equal bn minus nu kn squared. Yeah. So this is the full shell model of the Navier-Stokes equation. So what you can see is that the coefficient A can always be set to 1. So the parameter A can always be set to 1 by a change. So what you do, you can make a change of variables which keep just the same so if you take un to be equal nu un divided by A, no? Does work? Yeah, it works. So if you do this, then A becomes 1 in the new system. Just check it. So if you change variables, you can just put one of the coefficient to 1. So A will be, so we set just A to 1. So now what is B and C? So what is B and C? You can fix by trying to recover some conservation laws. So let's the main conservation law that we have in Euler Navier-Stokes system is conservation of energy. So in this, and conservation of energy is somewhat central for the turbine. So let's try to mimic this conservation law, but on the level of the shell. So the conservation law of energy. So for this, you have to define energy, and remember energy, which was defined as 1/2 of the just kinetic energy in original space. So for the shell model, by similarity, you can just define it as a sum of squares of the shell speeds, just in the same way. And now let's try to see that to answer the questions that when E is conserved for ideal system. when viscosity is 0. Okay, so how we do it? Just differentiate it with respect to time. So now remember that the sum ddt. Remember that square of the norm is un star un, right? So you can now differentiate one and another. So just remember that you're doing this with a complex number. So the answer will be sum over n, real part of un star dun dt. So this is the result. And now dun dt you use from equations shell model. From equation of the shell model with nu equals 0, so it should be implicit. So it becomes sum over n of a real part un star bn, right? And now use using the Goi model formulation for the bn, what you get is a sum over n real part. So then comes just term by term. I a kn plus 1 un plus 2 un plus 1 un star plus I b kn 1 un all stars, no? So this sum, and you can now recognize that all sums are actually all the same, because you can, if you here write n equal n prime minus 1, and here you can write n equal n double prime plus 1. So you will see that all sums are the same. So this is equal to the will become equal to sum over n real part I a plus b plus c by kn un plus 1 star un star minus 1 star. See, so the all sums become equal, and so it is 0 if a plus b plus c equal 0. So we get the condition, so the energy conservation condition is a plus b plus c equals 0. Okay. So as an exercise, check that the same condition follows for the Sabra model. For the Sabra model, there will be slightly just one extra step is that you have the three terms will not be just exactly the same form, but you will remember that this is a real part. So it means that you can take complex conjugation of any term and still give the same real part. So it's good exercise. You will see that there is slight complication when you move to the Sabra model. Okay, so we have this, and what is left is, but this is not enough, right? So we have just two conditions, and we have two conditions for three parameters. So we need one more parameter. Okay. I think I will not do it explicitly because this is much better to do it on a blackboard. So let's put it as a second exercise. Check that there exists a second quadratic, second implicit invariant. Implicit means that satisfied by the system with zero viscosity. Invariant of the form sum over A divided by C power n, absolute value of n squared. So just check that if you differentiate it, so with time you get identically zero for the implicit system. And now there are two interpretations of this invariant.
Alguém tá me ouvindo?
Sorry, I was for 1 minute off.
Okay.
Okay, sorry for the break. Okay, so there are two interpretations for this invariant, and the one interpretation is related to entropy. So remember that entropy we define as a half of the L2 norm of vorticity, where the vorticity is the curl of the speed, right? The vorticity brings, so if you try to make some analog of it in the shell model, that U should give rise to Un, and the gradient should give some analog of Kn. It should be quadratic in both and positive definite. So the way how you can make it, so positive definite quadratic in both variables, so then the shell model entropy can be defined as 1/2 of the sum of Kn squared Un squared. So this is just analog of this analog of the continuous form. And you can see that it is exactly the invariant that it's exactly this invariant when A over so it's exactly the same invariant. So it is conserved when kn square is exactly a over cn, right? But now remember that kn square is lambda n, so it's lambda 2n equal a over cn, which means that a over c should be lambda squared. And now remembering that a equal 1, you see have the c equal lambda minus 2. So this gives us the two-dimensional shell model. Yeah, because entropy is conserved in two-dimensional shell model, in two-dimensional order equation. So it means that whenever we conserve energy and entropy, it's the same model that the Euler equations for the fluid in two dimensions. So what we have is that A equal 1, B should be minus 1 minus C, and C equal lambda minus 2. So this is complete definition of the model. Another interpretation of this term is can be the helicity. Helicity is that important quantity that which is integration between the scalar product of vorticity by, so it's a projection of vorticity on direction of velocity. Now remember that it is again that vorticity is a curl. And now when we make a shell model analog, so we should put analog of we should put un on a place of u and kn on its place of gradient, and it should be not sign definite. So it can be as well positive or negative. So the analog of the shell model vorticity can be constructed by taking integral or integral sum of the, so we take minus 1n in power n in order to for making it sign indefinite by kn in absolute value un squared. So again, it is exactly exactly this quantity that we considered when a over c is equal to what? Minus lambda. So it is conserved when a over c n equal minus 1 n kn. Now remember that kn is lambda n, so it's minus lambda n. So or a over c should be minus lambda. Correct. Okay. So what we have for a equal 1, so what you have c equal minus 1 over lambda. So the 3D shell model, so shell model for three-dimensional incompressible flow is correspond to the a equal 1, b equal minus 1 minus c, and c equal minus 1 over lambda minus 1. Okay, so this is another shell model. So now we can just finalize our results to the final form of a shell model. Have the following form. So we have shell numbers. which are integer numbers. So these shells are labeled at 1, 2, 3, 4, and so on. Shell wave numbers. Where usually lambda is taken as 2. Shell velocities, which are complex. And the equations which have the form du dt equal bn minus nu. Just a second. Minus nu kn squared un, so this un. Sometimes people add forcing, the forcing term. Force, this is viscosity, and this is quadratic non-linear term. So everything is inside this quadratic term. So the model is defined by this Bm. So and Bn can have two different forms, which is in one case it's I kn plus 1 un plus 2 un plus 1 kn un minus 1 star, which correspond to the Ledger-Ohitani-Yamada model, or Bn is kn plus 1. Where complex conjugation is just put in the different places. So this is called sobre. And there are two different models in the two-dimensional. Model that correspond to two-dimension is where A, B, C parameters are taken as 1, minus 1, minus lambda minus 2, and lambda minus 2. And in the case of lambda equal 2, it becomes 1 minus 5/4, 1/4. Or in the three dimension, the shell model become 1, 1, minus 1, minus 1 over lambda, minus 1 over lambda. Or in the case of lambda equal 2, it becomes 1, minus 1/2, minus 1/2. Then the last part, which is important, is the boundary conditions. We need boundary conditions. So boundary conditions mean that for the boundary conditions correspond to large scales. Remember that scale is lambda minus n, so we consider large scales are those which have a non-positive integers. And we can just, the conventional way is just to say that all velocities are 0 for n smaller or equal than 0. And this summarizes the whole shell model. And this shell model surprisingly gives a lot of properties of the original Navier-Stokes equations with many different analogous features like existence, uniqueness, a lot of properties of turbulence, blow up, and all kind of things. So what we are going to do is to start on Friday. We will study what happens with the blow up. So how this blow up occurs in the shell model. So I think that's all for today. And see you on Friday. Friday, I don't know if I will be giving lecture at IMPA or not. So please check, or I will write it on my webpage. So either it will be linked on a new Google Meet, or I will just be giving lectures usual. So see you Friday.
Alexei,
Yes.
I have a question.
Sure. Mm-hmm.
Yeah, about sweeping effect.
Sweeping effect. So sweeping effect that that you know now. Well, sweeping effect is the effect which happens in. So it's an effect which because if you stay at the same place in space and consider small scale effects, you have a problem because everything is swept by large scale motion, right? So certainly sweeping effect is not captured by shell model. So this is I think that probably this is one of the main weaknesses of shell model. Well, it's not so much a weakness, but it is when people say about what shell model does not capture is the sweeping effect, and we will be talking about this later.
Okay.
Yeah,
Thanks.
so sweeping effect cannot be captured by the shell model. Okay, any questions? All right, so see you Friday. Ciao. I will stop recording if I understand where it is.